Now we are going to different problems. Aggregation. So we talk about partitioning of bridges. You have one bridge and you want to partition it. Now we are going to combine the bridges. You have 100 bridges, I want to make one out of 100. If you remember my previous slide, virtualization is just two things. Virtualization is either partitioning or combining. Partitioning or aggregation. So we just finished the partitioning of a bridge. Now we see how to combine the bridges. And so here is the thing. If I have 100 bridges, basically right now we need very big bridges, because the problem is now we have so many VMs, 10,000 VMs. Previously we used to have 32 port bridges, and that was big. I never had a 32 port bridge. The biggest I ever had in my home was 16 port, and that was big. But now these guys need 100 port bridges because there are so many VMs to connect to, and so on and so forth. And they actually need 1,000 port bridges and 10,000 port bridges. So how do they make it? They take little bridges and combine them. I will talk about 4 solutions in the next few slides. The first 2 are proprietary from Cisco, and the next 2 are the standard from IEEE. And I thought it might be okay. They're slightly different, but this is where they started. They started with those Cisco things, and then the industry liked it enough to make a standard thing so that everybody doesn't have to use Cisco technique or Cisco license or Cisco anything, right? So basically now there is industry standard. Actually, I think the first 3 are Cisco. Last one is standard. Okay? So let's talk about, First, this was not on the list, DVS. So VSS was on the list. So DVS was not even on the list. So DVS is first solution. DVS is distributed virtual switch, and this came from VMware. And VMware said that we don't have to have vSwitch in every hypervisor, or we could have VMs in a hypervisor, but the hypervisor could be virtual in the sense that the hypervisor could really be as if it is in every one hypervisor is in every machine. Okay, it is extending inside the machines. So that way, instead of having 500 vSwitch, we could just think of one vSwitch, okay, which is connected to all these VMs. So they combined all their vSwitches into one virtual switch, which is called DVS. The virtual switch is distributed, some pieces in this machine, some pieces in that machine, some pieces in that machine. Now we can control the whole. We can control the whole environment, whole cloud, by programming this virtual switch, this one switch.
One switch is divided into virtual switches which are distributed logically.
First of all, DVS is virtual. So it's not physical. There's no hardware in it. It's all software. Right? But basically, as far as you are concerned, you are the manager, you look at one switch and you say, well, this switch has 400 ports. Alright, port number 1 connected to VM number 1, port number 300 connected to VM number 300. So this is a big virtual switch. Instead of previously we had to say, machine number 10, port number 5 in that machine. Right, now we have this big switch with all the ports connected to all these VMs.
It is centralized or distributed in that sense?
It is centralized. Now you see why centralized is coming in. Is because, obviously you could have, standby and all that, but this centralization is the key word right now in the industry. Everything is getting centralized because you cannot do 10,000 distributed things. If you have 10 things, you can do distributed. Alright? OSPF, BGP, everything works with 10, 15, 20 things, but it doesn't work with 10,000 and a million things. Right? So distributed stuff this is the difference. Original internet was designed to be distributed because we had centralized network in those days. The current internet is designed to be centralized because we have distributed and that doesn't work. At least not in the control plane. So this is a centralized controller which many physical hosts. DVS couples the control, and so now this is where the decoupling of the data in control plane is started. So they decouple the control and the data plane of the switch so that each VM has a virtual data plane, virtual Ethernet module, but it is managed by the centralized control module. So what that means is that the forwarding table comes from this central place. It tells you, look, if you get a packet from VM1, it is going to packet VM5, send it this way. If you're going to send 3, so whole forwarding table in the switch is not learned, divided, and it is just done from this central place. That is DVS, right? Appears like a single distributed virtual switch, allows simultaneous creations of port groups on multiple PMs. And on this switch, you could say, well, I need 100 more ports. 5 on this machine, 10 on this machine, 3 on this machine. Right? And provides an API so that other networking vendors can manage vSwitch and vNICs. And now everybody, when they do something like this, which is, like their proprietary, they make sure that everybody else follows them. So they made a standard API so everybody else can do it. Everybody else is following. Cisco is following. HP is following VMware.
Is that equal with only one single physical network, a NIC?
No, it could be in a computer sitting in the central office.
It's like server.
It is a management station. It could be a virtual machine in a server too. I mean, doesn't matter how it is implemented, but it is controlling all the ports. The thing is, this is not physical hardware. This is not something that you have to go and buy. Yeah, you have to buy it from VMware, but all they send you is a disk. Alright, so this is DVS. You already see that DVS is basically aggregating all the vSwitches and making it look like one. Well, Cisco went one step ahead. They said, why don't we take physical switches and make them look like one? Alright, and that is called VSS. Virtual switching system. You can take 2 physical switch and let them look like one virtual switch. Now this is again a thing which is industry wide, but the name is different. This name belongs to Cisco. Other companies like Enterasys has virtual switch bonding, and every company has their own name, so I don't want to confuse it too much, but this is implemented in the firmware. So basically these switches have to be modified to be able to do this. Basically what it is now they have one control plane. Only one control plane is active and the data plane capacity is doubled. So whether you send the switch 10 gigabit here and 10 gigabit here, you can get total 20 gigabit coming in. As shown here, there are 4 links of 40 gigabits coming in. Okay? And they look like going to one switch. And both switches are kept in sync. So there is a link in between them and they are kept in sync to enable inter-chassis stateful switch over. You know what that means? Stateful means both switches know exactly what the tables are, where traffics are going and everything else. The whole state is in both the switches at the same time. And switch over. So if this switch fails, this one can take over the whole thing. Now what will happen is though, these 20 gigabit will not get there because this switch has failed. But whatever is coming in will go to the right place. Generally both of these links will be going to the same host anyway, as shown in the next picture. So generally what you do is you take a switch or a host or whatever that is and connect them to 2 switches. Alright? And if they are going to one switch, then you make a link, what we call link aggregation. Right? So if you have 3 links going to one switch, you make a link aggregation, which we call link aggregation control protocol in IEEE. But in Cisco terminology, it is called port channel. Port channel was before IEEE did this, so that is the original name VPC. Not PC so far, but port channel. And now you can take 2 which are going to different switches. The switches can become 1 and this can become VPC. Virtual port channel. So what it is that you have one 20 gigabit link going out from this thing which is physical as shown but could be virtual as well to this thing which is virtual. So this is a virtual. Now what the advantage of this is, obviously as you know, is in the spanning tree. If you are using a still spanning tree, for a spanning tree these 2 links will be blocked. With this one both the links are active because there is only one link here. Alright? And generally you will have two links going from this switch to 2 switches here, 2 links going from this switch to 2 switches here, and then they will be, instead of doing that, it will look like this to the spanning tree, and all the links will be used.
As a previous we have learned that LACP something
Yeah.
link
Link aggregation control program, yeah.
What was it related to this?
Okay, so this is link aggregation. The only thing is IEEE did not define this kind of combination. Okay, so the link aggregation is same as port channel. You can go from one physical to one physical. Alright? And IEEE did not say that you cannot do this, because if you make this one virtual, then this is link aggregation. Right? From physical to one virtual. So the difference between LACP and here is that now we are combining the bridges into one. Virtual bridging was not there when this thing was. So as we go to the last slide, IEEE has come around and allows this. But when this thing was done, VPC and VSS was done, at that time there was no IEEE standard. Oh, they had the standard for LACP, but they did not have this whole combining the bridges thing. So what is new here is combining the bridges, combining physical bridges into one virtual bridge. Yeah.
Does this virtual force channel make this one virtual switch have one priority, because they were both two physical devices?
Yeah.
With two MAC addresses, two priority levels.
Yeah, MAC addresses are still there. Let me tell you, MAC address do not belong to this switch. MAC address belong to the interface, to the port. Still, the number of ports has not changed. For example, there are 3 MAC addresses here.
MAC addresses will be there.
Yeah.
To make this work like this, for aggregating rather than blocking off channels,
Yeah.
this switch should have one single priority. Otherwise, both switches inside will be...
Okay, now again let me clarify. Priority does not belong to the port. Priority belongs to the traffic. Alright, so having said that, when they advertise as one link. So when they send out a spanning tree message, they will say, I have a link of 20 gigabit to that switch.
But when route is nominated...
Yeah, the route will be nominated based upon the distance. So everybody who is here, they would rather take a 20 gigabit than a 10 gigabit.
So for that purpose, this acts just as a
one link, yeah.
Switch and
one switch and one link, yeah. Yeah, that's why the links are not blocked. Alright, okay, so actually I switched this slide and then I was trying to explain. So I was trying to explain first two concepts. First concept is virtual switch system, which means you can take two switches and make them one. And second thing is virtual port channel, VPC, which means that you can take the links going to two switches and make them look like one. So this is VPC, and before that was PC, was port channel. Now this is virtual port channel. So this combined switch is called VPC domain. Each member of the VPC domain is called VPC peer, so there are two peers. And VPC peer link, which is the link between them, is used to synchronize, which as before. And all learned address step cable are kept synchronized among the peers, and one peer learns it and the other sends it to the other one else. Anyway, so you could have more than two also, right? So this is what basically it is, that you can combine as many switches as you want, and the links you can combine them. Once the switch gets combined, you can combine the links. Alright, and that is called virtual port channel. And this term is used so much in the industry that you really need to know this term, and that's why that was one reason that I put this slide here, even though IEEE has something else. But DVS, distributed virtual switch, throughout the industry. UPC, VPC, throughout the industry. VSS, so I mean, like VSS may not be that popular, but VPC is. So you really need to know these terms. VPC allows aggregation of links going to different switches. STP does not block links, all capacity are used. Unlike VSS, maintains two independent control planes. Independent control plane means in-service upgrade. So basically what it is when you do VPC, there is a little bit more than the VSS, and this is a fine point, technical point, and if I wish I can explain it, but I'm going to try to explain to it, is that in the other case, one switch basically doesn't learn anything, doesn't do anything. In this case, it also learns, it has control plane and it synchronizes with the other one. but it allows you to do in-service upgrade. So you could take out one switch and then you don't have to take any service off. Anyway, so this is a little bit difficult to explain, but anyway, let's move on to the next issue, which is the fast back to STP, which means that if when you take out one switch, then it is like STP. Then this switch has to announce that I have 2 links and so on and so forth. And so it's fast back to STP. So it is not really used for very large domains. Large domains means 1,000 port switches are combining 1,500 switches or combining 5 switches. It's small, maybe 2, 4, 3 switches. Okay. VPC is Cisco proprietary, but other vendors have similar technologies, e.g. SMLT by Nortel. Nortel is no longer there. Multi-chassis link aggregation, MC-lag by Alcatel, but there is no standard yet, even today. It's all being used, but not having no standard. Then, one more technology which came from Cisco is fabric extender. And this is getting even closer to combining. Basically what they did was they put some really simple boxes called fabric extender that didn't have very high powered CPUs. All it had was very simple ports, just like your home ports, very cheap, very simple ports, but they were controlled by a parent switch which had a very high powered CPU and could manage 1,000 ports. Alright, so you buy a very high powered switch and you buy lots of cheap, these fabric extenders, and then you can make a big switch with lots of ports. FEX consists of ports that are managed by a central remote parent, L2 fabric extenders, which are 48 host ports. You can buy these extended 48 ports, connected to a parent switch via 4 to 16 10 gigabit interfaces. So you could have 4 to 16 uplinks here. Parent switch provide a virtual switch with 576 ports. So you see how do you get 576? You have 48 host port, 48 ports here per fabric, right? And then you connect to 16. Parent switch has 16. 16 times 48 is 576. This is called chassis virtualization. Chassis virtualization because we have physical chassis which is separate. Everything is physical here, by the way. You do have 576 physical ports where you can plug in, right? But they're not in the same chassis.
Here is a fabric channel.
Oh, there is no fiber channel. Okay, all right. The word fabric started from fiber channel, but we already used it in PCIe fabric, and now Ethernet fabric. So basically, the fabric term has come from fiber channel to all the networking technologies. So we say network fabric, when we say Ethernet fabric, we mean exactly Ethernet network. There is no fiber channel. Alright, so this is chassis virtualization. All software updates, management, forwarding, control plane is managed by the parent switch. So these guys are very simple. Alright, and a FEX can have an active and a standby parent. So if you don't like one parent, you can have 2 parents. So basically, we need large switches, and Cisco came up with this idea that we could have lot of ports and they don't have to be all in the same box. Ports could be outside the box, but the control and management will be in one box. So they came up with the concept of fabric extender. Fabric extender is an empty box with a connector in it, with some intelligence, but not too much. Okay. So all the intelligence, actually most of the intelligence comes from the parent switch. So parent switch tells it, this is how you basically, it may not really clear as to what it tells, but it's basically it will simply say that make 2 copies of this packet and send it to 2 people. That's the kind of thing that will say, not too much more. So you have fabric extenders which have ports in it, and then you have the parent switch which controls those ports, remotely controlled ports. And so the whole thing looks like one switch with many ports. So we saw the number here. If you have 48 port extenders and you have 16 of them, so you will have a 576 port switch. And good thing is that there is only one thing to control, so you don't have to worry about whether this how to control that part. You don't have to control 16 switches, you just control one switch. Actually, you don't control 17 switches, you just control one switch. And so you could have two parents, which is not shown here. So this extender could be connected here as well as to another switch. So there will be two parents. If this parent goes down, you continue to work with the other parent. So that is not shown, but you could have two parents. And the way it is done in the data centers is that you will have extenders in the rack. Each rack will have extenders, actually two extenders, just to be fault tolerant. And these extenders will be connected to the switches which are in the end of the rack. Alright, so this whole thing is one switch. This whole thing is another switch. So the fabric extenders are very simple boxes, just with simple ports in it, and the brain is here. So this whole thing acts like one switch. And if you use virtual port channels, VPC, port channels, VPC, that's a very common word in the industry, so you should remember that now. VPC, virtual port channels, then all the links can be active because this is the configuration. You have a server, each server is connected to FAX, and each FAX is connected to two switches, and so on and so forth. Now, if you do virtual port channels, these two will look like one. So everything will be active. Yeah.
So, is this how is this different from the end of flow topology?
Previous topology?
Yeah.
Yes. The thing is, this is different in the sense that these FEX are very cheap. So in the previous case, you would have a real switches here.
I mean, in the flow.
Or end of row, you will have to take lots of wires. Here you are not taking wires, you are just taking the wire from the FEX. So the FEX has maybe 16 wires coming to that, but only 1 or 2 going out. So this is still top of rack in terms of wiring. See, the disadvantage of end of rack was too much wiring. So this doesn't have too much wiring. No, they are not going together. One wire can bring all 16 ports. Okay, let me show it again. Here it looks like the number of wires is equal to the number of ports because there are 4 wires and 4 ports. That is not the case. Only 1 wire is required for 16 ports. I have shown 4 here because you may want 40 gigabit. You don't want 10 gigabit each, right? So this is just over provisioning. We have just put 4 where only 1 is required. And so you might have 16 ports here, but only 1 wire total here. You could have 2 wires if you needed more capacity. If you 3 wires, 4 wires, 5 wires. But if you put 16 wires, I think then you really didn't get any benefit. Right? So the number of wires is small compared to the number of ports. Alright, so here you see these wires are coming up and then only 1 wire goes to this switch and 1 wire goes to that switch. So 2 wires going out. Now you could double that, and so on and so forth. As much capacity you need, you could put. But basically the number of wires is still, smaller. Alright, so this was standardized by IEEE. And it is called Virtual Bridge Port Extension, VBE. Now there is no P there. Virtual Bridge Port Extension. And this is a very new standard, 802.1 BR 2012 with a capital B with a capital R, means it is a standard by itself. And it does exactly what we said before, is that you have a controlling bridge, you have extenders, and you can have a cascade of extenders. So you could have an extender, another extender, and so on and so forth. Some of these extenders could be inside a host. See, this is one host. So this is a vSwitch. So the vSwitches could act as an extender. The advantage of this approach is now you don't have to worry about VEB or VEPA because these ports are completely controlled by this. They are following all the policies. Okay? So you can see all the traffic, you can follow all the policies here. So these bridge port extenders could be real or virtual. It could be a physical box or it could be just a vSwitch. So now this combines both the DVS concept. Remember the DVS concept, distributed virtual switch from VMware, where everything was vSwitch here. That would be covered by the same standard. You could take lots of vSwitches and make one big switch out of it. That was the VMware concept, is now bridge port extension. Or you could take lots of physical ports like Cisco concept and make a bridge out of it. Both of them are covered here, and these could be cascaded. Any question about this? Now this standard is a big standard, and believe it or not, there is not much public documentation about this. It just came out, so I read the standard and I prepared 10 slides, just put one here, 9 are in the background. But this is where you need to go and read. If you need to know more about it, you need to go and read the standard itself. And I didn't want you to read the standard. This is probably too much for this class. But if in real life, if you are to implement this thing, you will have to go and read the real standard. If there are no questions, then we are end of this chapter at this module. 5 key points: that network virtualization includes virtualization of many things, starting with the NICs, bridges, routers, L2 networks, and so on and so forth. And in this module, we have just covered only one part. In the original picture, if you remember, there was a table we said in the beginning of this module. There was a table which said, how do you virtualize? So we haven't got into L3 and both those other things, right? But this is just some parts. And we talked about two kinds of virtual switches, vSwitches, VEB and VEPA. VEB is local loop, and VEPA is external loop. This is internal, this is external. Then we looked at SRIOV, which was the PCI stuff. In the PCI, you could have one NIC provide multiple virtual NICs. So you don't have to worry about hypervisor doing it or having CPU work on these codes. Okay, it is done by the NIC itself. Then we went through VSS today, or yesterday, last time, which allows multiple switches to appear as one logical switch, and vPath channel, which allows links to appear as one. Multiple switches links to appear as one. Fabric extension and virtual. Then last thing we discussed was fabric extension, which is the same, which is actually a proprietary technology. The standard is called Virtual Bridge Port Extension. Now I missed the word port here, but it is Virtual Bridge Port Extension, and that is VBE. And then basically you can create large switches. Now reading list. Some of these white papers are easier reading than the book. That's why they are ordered like this. And these are PowerPoint presentations. Some of these are PowerPoint presentations that also provide more details. But so that is that for SRIOV. Another thing is IBM Red Books. I don't know how many are familiar with IBM Red Books, but IBM Red Books are really good because they're free and they're 400-page books. Okay, and they're really thick books, but they're free online, so you can just download them. This is a 654-page book, and I find them they're very well written in some sense. I mean, obviously they're vendor books, so they go a lot, and with their product you have to just read it out of it, but they are good topics. So that is, then there is anyway, and then there is an excellent presentation in SNIA. This is a PowerPoint PCI. So I wanted to read that. And anyway, so, and there is some information on the Wikipedia.